So, our final speaker, Gijs Heuts, who's going to tell us about the Koszul duality of En-operads and En-algebras. Thanks.
Thank you, Dave. So, since this is the final talk this week, I suggest that we thank the organizers. Been a wonderful week and very interesting and a lot of fun. Feel a little out of place. First of all, I haven't given a slide talk in ages, so I don't know how that's going to go. Also, there will be no memes. Book covers. I didn't make any pictures. Maybe Connor can provide some light entertainment during the talk and we'll get through it.
I'll be laughing and not betting the size.
Okay, thank you. All right, we'll see. Good. So, I want to talk about some joint work with Marcus Loont, and then there will be some other collaborators later. Lucas will be very angry if I don't mention his sorry. Right, let me fix some notation before we get started. So I'm going to write operads and spectra for the infinity category of operads and spectra. They're always going to be non-unital in this talk, so that means the zero term is zero. So I have no units. I will sometimes somewhat gratuitously switch between things like augmented algebras and non-unital algebras and not say too much about that. In practice, they're also going to be reduced all the time. So like, one is going to be the unit. Okay. And I'm going to be mostly interested in the En-operad for today. So if you have the En-operad in spaces, of course, you could make it an operad in spectra by just applying sigma infinity plus. And I put the little the NU up there to indicate that I made it non-unital. I just discarded the zero term. And I don't want to drag along this notation, so actually I'm just going to write the N for that thing pretty much all the time. All right. So as a jumping off point for this talk, I'm going to take the following not very interesting looking results, but it's going to be quite useful. I'll show you the kind of mileage you can get out of it. So it's a joint result with Marcus. So it says you could look at the functor that takes an operad in spectra and it assigns to that operad, well, its category of algebras. Okay, and you think of that as a category that sits over spectra via the forgetful functor. Okay, so O goes to algebra spectra, forgetting to spectra. And the statement is that this functor is fully faithful on En-operads and their desuspension. So if you don't know what this last thing means, then ignore it for now. I'll get back to that in a minute. But it's fully faithful on En-operads. Okay, so what's this telling you? It's telling you that you can manipulate En-operads by manipulating their categories of algebras. And for the second thing, we actually have quite a number of tools to manipulate En-algebras, maybe more tools than you have to correctly manipulate En-operads. Okay, so yeah, fairly innocent looking statement, also kind of formal sounding statement. I just want to stress now, I mean, it's not very formal. Like something goes into proving this. In particular, it's very specific to En-operads. This is very false if you, for example, include the infinity operad or the spectral B operad or something like that. It just doesn't work. So it's special to En. Well, it's special to a slightly larger class of operads, but we'll get to that. I'll try to talk about the proof of this towards the end. Depends on how time goes. But for now, I just want to show you how you might use such a theorem to prove some things about En-algebras. All right, let me maybe quickly mention, the punctuality in this result, which I didn't make very explicit, but I think you know what I mean. If you have a map of operads, then F here, then it will give an F upper star just by sort of restricting scalars on algebras, and that's the punctuality that I have in mind when I mention this functor here. Okay. All right, so let me quickly say something about these operatic suspensions because they'll play a role throughout the talk. So operatic suspension means the following thing. If I have an operad O, then there's something that I'm going to call its suspension, S of O. Confusingly, not the suspension in the infinity category of operads. That's not what it is. Suspension refers to something slightly different here. This SO is an operad that's rigged so that the following thing is true. So if you look at the free algebra monad for S of O, then it's just this thing that you build from the free algebra monad for O. Okay, so if I have the free O algebra monad, I can apply it to the suspension and then really nothing I can do. Yeah. Right. How do I? Oh, all right, okay.
Why can't restart mine so it happens?
Yeah, so good. Thanks, Niall. I'm glad you're enjoying the. You're free to leave, you know.
I want to see what happens.
Actually, trapped in that back of the strap.
Sorry, what's that?
Trapped in the throat.
Oh, yeah. You can't get past my. All right, okay, so what I'm doing is I'm just taking the free O algebra monad and conjugating it by this automorphism of the category spectrum. And that's the suspended. And it doesn't, yeah, you can debate to what extent this actually characterizes SO. Let's not do that. But this is the most important property that this thing has for me. All right, so maybe two facts about this. First of all, how do you actually describe this operad? Well, if you give this formula a little bit of thought, you'll conclude that the terms of this operad have to look like this. With just suspended copies of On, and the suspension, the exact suspension that you use depends on N. If to be precise, you just, this rho N is the reduced standard representation of sigma N on Rn, so you just portion out by the diagonal. So this is really a sphere of dimension N-1, but it has an interesting sigma N action, okay? The other fact is that the category of algebras for this SO abstractly is just equivalent to the category of O algebras. I didn't change the category of algebras. I mean, I'm conjugating by an automorphism of spectra, right? So that doesn't really do anything. So if you have an SO algebra, then you can conjugate back. You can just suspend the underlying spectrum, and that gives an equivalence of categories between SO algebras and O algebras. So same theory of algebras for this thing. Now, oh, this is a bit too much, yeah. Now let me just give an example of how you would apply the theorem, right? So what's an interesting functor that you can construct on the En algebra? It's the bar construction, right? So if you have an augmented En algebra, or equivalently a non-unitable En algebra, passing to its augmentation ideal, you could perform a bar construction, and the bar construction just eats up one of the E1s, one of the associative multiplications. So it eats up an En algebra and it spits out an En-1 algebra. And you can just try to apply the theorem to this. Now, there's one little issue. I mean, the bar construction is not compatible with forgetful functors, so you don't quite apply it to this functor, but I'll tell you what you do. The point is that using the theorem, you'll see, and I'll show you exactly how in a minute, you'll see that the bar construction essentially is just pushed forward along a certain morphism of operads. So I'm claiming the bar construction essentially uniquely determines a map of operads that I'll call beta. It goes from En to an operatic suspension of En-1. And I'm claiming the bar functor here is just this push forward functor beta freak that goes from En algebras to En-1 algebras. And this beta, again, let me just stress, it's uniquely determined by the fact that it induces this bar. So this beta here, this is exactly one of these, this color is not great, but okay. One of these wrong way morphisms that Thomas was talking about. So he suggested a construction using Goodwillie calculus. I mean, there are other constructions in the literature, of course. Chig Salvatore give a construction. May gives something that you could also call a construction. I always forget that these things are recorded. What was I going with this? Yeah, let me tell you how you actually construct this morphism, at least using the theorem that I gave. Okay. So, well, the proof is you do this. So first of all, you pass the right adjoints. Okay, so the bar construction, okay, you have to prove that it has a right adjoint, but it does, and I'm going to call it little omega. Should I get rid of this bar up here? I mean, I know that I just realized again that this content is being sent to a third party, so thank you. Right, so now you can read this. So there's a right adjoint to the bar construction, little omega. And it fits into a little diagram like this, if you think about it. It's not quite compatible with forgetful functors, but it's compatible with forgetful functors up to a shift. There's just a single loop here. The way that you check this, for example, is by thinking about the left adjoints. So that the bar construction on free En algebras essentially, it's compatible with the free functors up to a single sigma. So, okay, anyway. You get this thing, so you can't quite apply the theorem to this diagram because of this loops, but that you can easily fix using this suspended operads business. You just tack on this equivalence that I had before. So you look at En-1 algebras that's equivalent to En-1 algebras, and well, the equivalence was given by shifting on the underlying level. So now at least I've done something where here the composite functor is the identity. So now I have a diagram of algebra categories sitting over spectra by the forgetful functors. And I can apply the theorem, and the theorem implies that the top horizontal arrow in this diagram must be beta upper star for some uniquely determined beta. So there's your beta. And then passing to left adjoints, you get the thing that I claimed about the bar construction being beta shriek, at least up to some degree shifting. Okay. Okay, so this is a convenient way to characterize this wrong waymorphism because it allows you to prove stuff about it by proving stuff about just the bar construction for En algebras. And okay, lots of people have proved things about that. Okay, so let's pass to something a bit more substantial, maybe. Let's talk a bit about Koszul duality for En algebras. So, right. So if you say Koszul duality for En algebras, there are at least two possible things that you could mean by that. So the first is bar-cobar duality for En algebras. Right, again, it's something that's been around for quite a while. I mean, set up at maybe this level of generality in a nice way in higher algebra. What you can do is if you have an En algebra, you can perform the bar construction n times, just eat up all of the n different associative multiplications that you have over here. And the output, well, every time that you perform the bar construction, actually you pick up an E1 coalgebra structure. So if you do that n times, you end up with an En coalgebra. So the bar construction can be interpreted as a functor from here to here, and as such, it has a right adjoint, and the right adjoint is given by the dual construction, it's the cobar construction. Okay, so there's some duality between En algebras and En coalgebras, like so. The other thing you could do, I mean, there's this general notion of operatic Koszul duality, which you could just try to specialize to the case of En. So for any operad O, you can always form something that you could call the Koszul dual cooperad. And again, it's a bar construction. So you think of O itself as an E1 algebra, as an associative algebra in the category of symmetric sequences with respect to composition product. So it being an associative algebra, you can perform a bar construction, and it gives you something that's then a co-algebra in symmetric sequences. That's what a co-operad is. So this is also the bar construction. I've written it BO instead of bar O just to not get confused between these two different things going on. Like one is about algebras, the other is about operads. Okay, so you can always do this, and so you always, for every operad, you get a Koszul dual thing, like, okay, this is a co-operad. You could also take, like, the term white spanning white, the dual, to make it an operad if you wanted to do that. The point is that O algebras are always canonically related to co-algebras for this dual BO. And so there's always some adjoint pair that you can write down, which is between the category of O algebras, infinity category of O algebras, and the infinity category of co-algebras for this dual, this bar O. And the functors that you get, one nice way of thinking about them is as, well, it's a form of, or it's the form of homology for O algebras. This is actually the universal homology theory for O algebras, if you think about it. But I'm calling it indecomposables here. So whenever you, for any non-unitable operad O, there's a reasonable notion of indecomposables for O algebras. For example, you could write down this indecomposables functor as the left adjoint to the trivial algebra functor. If you take a spectrum, equip it with the trivial multiplications. Left adjoint to that, but the claim is it actually naturally, this indecomposables object naturally acquires the structure of a BO coalgebra. So maybe like some examples that might be familiar. If you were to do this to O as the commutative operad, and this thing I'm calling indec O is the thing that's usually called TAQ, the topological object cloning, or the cotangent fiber, or I don't know, there are probably other words as well. If you were to do it to Lie algebras, then this is always some form of Chevalley-Eilenberg homology. Okay. If you're doing it for E1 algebras, then it's a form of the bar construction, which is, that in itself is a form of Hochschild homology, at least with coefficients. It's like to reduce, whatever. Anyway, so this indec usually produces familiar forms of homology for your given theory of O algebras. This thing about it being a universal thing, that's a theorem of Bastera and Mandel. They proved that this indec functor, if you think of it as landing in spectra, it is the stabilization functor for the category algebra spectra. So in that sense, it is the universal homology theory. Okay. Anyway, so you have this indec functor. It has a right adjoint, which again is given by a completely dual construction, and I'm calling that primitives of BO coalgebras. All right. Right. So this is something you can always do for any operad. In particular, you could do it for the En operad, and you could ask, well, okay, I mean, like, what's going on, right? Why do I have two duality theories for En algebras? They're probably the same. So that's always, I think, been the expectation as long as this whole game has been around. So in the special case where you take O as En, you expect these pictures to coincide, like these should be in some sense the same duality. Let me write that down. The expectation is that you want sort of informally written it like this was the first picture, this is the second picture, and you expect them to somehow be the same. So in order to make sense of that statement, if you want these to be the same, at least you should start by making the terms in these two little diagrams the same, right? So, okay, if I said O is En, then that's not a problem on the left, but on the right, here I'm looking at co-algebras for En. I could think of that as co-algebras for a co-operad, namely the Spaniel-Whitehead dual of the En-operad. And here I have co-algebras for this co-operad, sorry, BO. Okay, so if these are supposed to be the same, then at least this co-operad En dual should be the same as this co-operad BO when O is En, at least up to some shifting, right? And there's the possibility for some degree shifting going on. So if you think about this carefully, you'll come up with the following expectation. I'll get back to this degree shift later if you're not familiar with where that comes from. But at least, like, to make these pictures look alike, you should have something like this. You want the bar construction on En to be essentially En again, up to Spaniel-Whitehead duality. This thing is a co-operad, and up to some shifting. So that's like the I'm saying expectation, like, I mean, this was originally when bar-cobar duality for operads was introduced by Gepster-Jones, like they proved this in their paper when you're working in this vector spaces over the rationals. So later Frese proved this work over the integers, chain complexes over the integers. And then in the context of spectra, this is a theorem of Ching-Salvatore, okay? This was an outstanding problem for quite a long time, and then Michael and Paolo resolved this in 2018. About now. Okay, so this expectation is true. So that, I mean, that's a strong suggestion that also, you know, this expectation here should be true. And there's a second later proof by Connor, who also proved this what people now refer to as self-duality or self-Koszul duality at the EM. So these proofs are very nice. So this is true, but one drawback of the situation is that they don't quite do this. Like, it's not clear from those proofs how this self-duality En actually interacts with bar-cobar duality for En algebras. So I want to suggest a somewhat different way of looking at these results. So here's a different flavor of theorem, which is closely related to these previous results. But theorem is there's an essentially unique equivalence of co-operads between the bar construction. So this equivalence, again, this was already there. It's the theorem of Ching-Salvatore, but I'm claiming there's an essentially unique one that makes the following diagram commute. So here in this diagram, again, I have this n-fold bar construction that relates En algebras and En co-algebras. And here I have this other one, this operatic form of Koszul duality that takes En indecomposables and will land in co-algebras for this bar construction. Okay, so this was the first type of Koszul duality. This is the other type of Koszul duality. I'm claiming there's essentially a unique gamma that you can use to make the two the same. Like here on the right, there's nothing going on. There's just this degree shifting. So this arrow you can pretty much ignore. It's not very interesting. Here is this gamma that makes an equivalence between the bar construction of En and well, co-algebras for the bar construction of En and co-algebras for this suspended En operad. Should have been a check here somewhere. Okay. Right. So first of all, I'm claiming that this particular gamma it makes these two forms of Koszul duality compatible, and moreover, that compatibility characterizes gamma. So that the proof of the theorem is going to go the other way around. We're going to produce gamma by using that first theorem that I had and sort of requiring that this works. So in other words, I'm saying that you can deduce the self-duality of En from the existence of bar-cobar duality for En algebras. And if you deduce the existence of gamma in that way, then you've rigged your story so that they must be compatible. All right. So let me try to indicate how the proof of this result goes. Let me maybe stress the nature of this proof is quite different from the existing ones. So there's essentially no geometry in this proof. So the existing proofs of the self-duality of En, they rely on things like the existence of the Fulton-McPherson compactifications of configuration spaces, and they have something to do with the geometry of those spaces. Like essentially those exhibit a form of self-duality with respect to Alexander duality or Poincare duality, and that somehow features quite prominently in those proofs. This proof actually is going to be very sort of categorical algebraic, so much more formal. So it's saying that, like this geometry is really nice, but it's not necessary to prove the result. So you can be happy about that or sad about that, and it's up to you. Right, so I'm going to start with actually replacing spectra with the category of graded spectra for now. It's actually positively graded, well, include 0, but category of graded spectra, that's still, you know, symmetric and ordered in the usual way, by a day convolution, let's say. And I'm going to look at En-algebras in this category of graded spectra, and I'm going to call such a thing connected, just if its augmentation ideal is concentrated in strictly positive degrees. So I'm not referring to connectivity of the underlying spectra, that doesn't play a role. I just mean, maybe I should have said weight connected or something like that to stress that, but this connected refers to the grading here and not to the connectivity of the spectra. I'll say something similar for En co-algebras. So you can investigate bar-cobar duality for En algebras in this graded setting, and that turns out to make things a lot easier. So if you look at bar-cobar duality, for these, like this here denotes connected graded En algebras, this is connected graded En co-algebras. You still have your bar-cobar adjunction, and here it's just an equivalence. Okay. Now, I've had a little trouble sort of pinpointing the history of this theorem. Like this is one of these things it's like folklore in Boston type of theorem. Probably also in other places, I don't know. But like, if you try to chase it through the literature, the earliest one I can find is Han Wilson, but you have to be a bit careful. It's not in the published version. So Han Wilson originally used Koszul duality for En algebras, and then the referee, who will not be named, pointed out that that was not necessary, and so they removed it from their paper. But if you go to the first archive version, they have a version of this in the appendix. There's a version by Krause somewhere where he does E1 algebras, but actually the general case formally reduces to the E1 case, so Krause's result is also essentially good enough. If you go to the appendix of Robert Berkman's paper on multiplicative structures on Moore spectra, he also has pretty much exactly this in there. Although Jeremy was just telling me he's also going to remove that because apparently it's not necessary. So who knows where this will stabilize. It is true, and it's also, you shouldn't think of this as being something that's extremely difficult to prove. Without no attempt to insult any of these people. Robert's not going to care what I say anyway. So the point is, if you're trying to prove a result like this, like you always end up at some point having to commute a bar construction, which is a geometric realization, past some cobar construction, which is a totalization. And okay, you cannot usually commute infinite co-limits past infinite limits in the category spectrum. That's where you ordinarily get stuck when you try to prove something like this. The point here is if you're working with graded connected objects, and all these bar constructions and cobar constructions that you're doing will be in every fixed degree will be finite limits and co-limits. And so all these issues with commuting, they go away. Like for example, also if you look at the Francis Gatesworthy paper on operatic Koszul duality, you see exactly the same sort of thing happening. Like they sort of pass through a setting where these limits and co-limits become finite, and then it becomes a very formal diagrammatic argument. So the same is true here. Again, I'm not like, I just want to stress, I'm not hiding any geometry under the rug here. Like you can formally reduce the proof of this to an E1 case where it's really a very direct diagrammatic argument. Okay, so bar-cobar duality works very well in this graded connected setting. That's the upshot of this somewhat long rant. A consequence of that is the following. Let me maybe quickly go back to this previous slide. So to point it out over here, I should put these two pictures in the same, but the point here is, you know, this category here, it's comonadic over graded spectra. Like there's some associated comonad here, which is just the co-free co-algebra comonad for En. And well, by this result here, you know, this thing is also comonadic over graded spectra, but here the associated comonad is a priori something different. It has to do with the bar construction of En. Okay, so this, you can read this result as saying that these two different comonads having to do with the co-operand En and the bar construction of En acting on graded spectra are actually the same comonad. Well, that's what I've written over here. So this is the sort of the co-free co-algebra comonad for En dual. And this is the co-free co-algebra comonad for the bar construction of En acting on this category of graded connected spectra. So the notation that I'm using here is that, you know, for symmetric sequence A, I'm just writing sim A for the thing that looks like the free symmetric algebra, like the free E infinity algebra, but with coefficients in this symmetric sequence. And just adding up all the extended powers that you would associate with the symmetric sequence A. All right, so these two things are the same. Well, that's nice. You is now you could apply the theorem, maybe not quite in the form that I stated it, because I'm saying something about comonads rather than monads now, but okay, not a big deal. I forgot to say something. Secretly here, like the suspension, you've seen it appear here. So secretly under the rug, I have used this equivalence that the En indecomposables, at least on underlying spectra, are related to the bar construction just by a shift. That's not a. I mean, that's a well-known fact about En indecomposables that I'm using. Anyway, this is secretly where this n-fold suspension here. This is where this n-fold shift in the En dual here is going to arise from. But okay, so you have this equivalence of comonads now, and you can apply a form of the theorem that I started with. So it will tell you that an equivalence of comonads like this has to arise from a unique equivalence of co-operads like this. Yes.
I was wondering, like, if I'm just doing like between O and BO, then like I assume I'd get some abstract version of this equivalence you've written here in between. But I just am like.
Well, for general O, I don't have these two different forms of Koszul duality that I'm comparing. Like the theorem that I started with here, I put En co-algebras. So like if you said I put O algebras here and BO co-algebras here, then I'm going to end up with the topology sim BO is sim BO.
So there's in the junction you've written down is not appearing the other thing I'm comonadic over. What is that? I think I understood from what you first said. Right?
Oh, okay.
Yeah.
I'm just using like co-bar duality for En algebras, and I'm not using operatic duality here. So this is the thing that's available for En that's not available for general O. And then I'm using that, like, if you look at the comonads on graded spectra induced by these two, that's where you see like the bar construction of En arising. It arises from, if you think about like the functor that goes from here down to graded spectra by first going here and then forgetting, that's the n-fold bar construction, and just that functor, that's essentially the same as the indecomposables functor. So that tells you that comonad that you're getting must be the comonad you got from like indecomposables En after trig En, and that's the bar construction of the En.
Okay.
Does that make sense?
I think so.
Okay. Other questions at this point? Just moving a bit fast. All right. Right, anyway, so the conclusion is, as I said, like, something like this, it must come from a unique map of co-operads, and that, well, the map of co-operads is have to be equivalent then also. Okay, so that's where you get your gamma, and also where you get your uniqueness of that gamma. All right, so okay, it's a very formal sort of diagrammatic way of proving this Koszul duality. So the point of this is not to give you yet another proof of this self-duality, but just to make it so that you can understand how it interacts with duality for En algebras, and that will give you good control over this map gamma and this map beta that I had earlier, this particular approach. And what I want to do is illustrate some consequences of that, like how you might use that to say some possibly interesting things about En operads. Okay. So one thing that falls out of this particular setup rather easily is something that was related to a question that Thomas asked in his talk. Well, his beta was constructed in a different way, so I'm not answering that question, but I'm saying for the beta that I advertised earlier, it's pretty much immediate that it is actually the Koszul dual to this ordinary, like the obvious inclusion from En minus 1 into En. So what I mean by this phrase, the Koszul dual, I just mean the following diagram can use. Okay, so I can take beta and do the bar construction to it. So that's going to be a map like so. And I can look at these equivalences gamma that I got from my previous theorem. So these go between bar construction of En and this suspension of linear dual of En, similarly over here. And I'm saying that this diagram can use. So if I put these gammas here, these equivalences, then the bar construction of beta here corresponds to iota here, or maybe the Spanier-Whitehead dual of iota. So in this sense, beta and iota are Koszul dual. The way that you see this is, well, because essentially, like I've characterized both beta and gamma by what they do to En algebras, what they do on algebra categories. So beta is built out of the bar construction. Gamma is also built out of the bar construction. So if you just write down some commutative diagrams of functors with bar constructions in them. Like there's one that matches exactly this little diagram, and you'll see that because of that diagram of functors commuting, it's just some bar constructions. Actually, this diagram of the co-operand maps also had to commute. Okay, so it's sort of formal from this setup to compare this particular morphism that has to do with the bar construction to this Koszul self-duality, the En-operads. And yeah, this is a very convenient feature to have because now you can start playing games with this data. So one thing you can do is if you have this data, you can start iterating it, right? It gives you these maps between operads. I slightly re-indexed them, so I started desuspending these En-operads here. You can take the inverse limit along all of these things, and because you know that beta is Koszul dual to the inclusion, you know what this inverse limit is. It will have to be Koszul dual to the co-limit of the iotas. Right, so this limit, this particular limit here is Koszul dual to this particular co-limit here. This co-limit is E infinity. Here, this is my font color. That's great. I'll use a different one next time. This is E infinity, and so this limit here will be, well, it's by definition it will be the Koszul dual of E infinity, and that's the definition of the spectral E-operad. Again, like the fact that you can get the spectral E-operad as an inverse limit of the N-operads, that follows from this Ching-Salvatore theorem. Take this diagram, you could take its Koszul dual. The thing that I'm going to exploit here is that I know that these maps are this beta that has to do with the bar construction. That's an extra piece of information that's we need to use later on. Okay, so what I want to do is sort of advertise how you might use some arguments like this to say things in the style of the Poincare-Birkhoff-Witt theorem, but then not for ordinary Lie algebras, but for spectral Lie algebras. Okay, so I'm going to use the fact that I have good control over these beta maps and over how they interact with the Koszul duality to prove some theorems in that style, in a very formal way. So this part is joint work with Omar, Angeline Camarena, and Lucas Brandner, who I mentioned before. There you go again, Lucas. Right. So on the previous slide, in particular, the diagram that I had, well, it induces morphisms from the Lie operad to all of these En-operads, or maybe they're desuspended n times. So here I've just thrown the suspension coordinate to the other side. So I have these morphisms. Again, I mean, I could have gotten morphisms like this already from the Ching-Salvatore theorem, and you can do this construction. I'm going to use the fact that they come from these betas. So if you have a morphism of operads like this, then what you can build a functor on algebra categories just pushing forward along these morphisms, right? So I can take a spectral Lie algebra, so I'm just using this notation for the infinity category of algebras over L. I can push it forward to En, so to produce an En algebra out of every spectral Lie algebra, and you should think of that as a universal enveloping algebra construction. I'm going to call it UN, and call it the En enveloping algebra. So this is, there are different constructions of this already in the literature. Like there's a paper from Ben Knudsen where he constructs universal enveloping En algebras for Lie algebras through very different methods. Like he uses factorization homology to do this. And once you have the result of Ching-Salvatore, so once you have access to an operad morphism like this, then you can write down a functor like this. Actually, this is not claiming any novelty in this construction. You're just claiming a little more control over this construction. So here's something you can do to get going. So you start by looking at this little square of operads and operad maps, right? So again, this iota, this is the usual inclusion. Here also, on these suspended operads, and vertically I have these beta. So first of all, I'm claiming this square of operad maps is actually a commutative square. And again, the way that you would check that is by checking that on the level of algebra categories. And there that's a simple thing to do. Okay, so maybe I didn't draw it in this square, but maybe worth mentioning is actually the diagonal arrow here is also a familiar thing. It's the thing that's called the suspension morphism of the En operad. So any operand has a suspension morphism, and it's exactly the thing that implements the suspension functor on algebra for that operand. Anyway, okay, so this thing commutes. Actually, this thing, it does more than commutes. This square has a rather special feature, namely, it's what I like to call a composition square. So what that means is, in this square, what you can do is, well, you can use this square to interpret this operand here as a right module over En, and you can interpret this operand here as a left module over En. once you do that, you can form the relative tensor product with respect to the composition product. Okay, so you form this sort of balanced tensor product here. You get a map just by commutativity of this diagram. You get a map from that symmetric sequence here, or you still think of it as a bimodular if you wanted to, but from this symmetric sequence to the final object, so this SEM. And I'm claiming that actually the resulting map is the equivalence of operads. Okay. Maybe important to stress, I am not claiming that this thing is a push-out square of operads. In fact, I'm claiming that it is not a push-out square of operads. Okay, so a composition square is not the same thing as a push-out square. That's important. Also, this notion of composition square is not symmetric. Now, I put this thing on the left, I put that thing on the right. That matters. Okay, the composition product is not symmetric, and you're not allowed to flip the variables here. You just get nonsense.
Maybe you said, is it supposed to be obvious that the composition is an operand?
No, that's another.
You said it's an equivalent of operand. Right?
No, I said it's an equivalence of bimodules.
Oh,
Did I say, if I said it was an equivalence of operads, then I was. That's not clear. I mean, a posteriori, you conclude that this thing had an operad structure because of this. But it's not clear that if you write down squares of operads like this, that such a thing should be an operad. I mean, that's one of the things that I'm somewhat confused about here. Right, so what was I saying? I'm not a push out of operads, and well, I'll get back to that observation later. But this thing is true. I mean, how do you see that? Well, you could. There's several things you could try. You could just try to compute, right? So maybe easiest thing to do to check such a thing is just first rationalize everything. The En operad becomes rather simple. It's just the semi-direct product of a commutative and a shifted Lie operad. And you, in that case, you can really do this calculation. Like essentially, you know, this map here. So this is related to a question Muriel asked at some point. Like this will identify the comms in the two and be 0 on the Lie. And this beta is actually, it would be 0 on the com factor that identifies the Lie things in both. And so these two maps have sort of a complementary effect. If you then compute this push out, you'll see that again, you get something that looks like com semi-direct Lie and things are exactly on the right degree. So you could do a homology calculation to do this, and you can even do that homology calculation integrally. And you can set up some spectral sequence that computes the homology of this bar construction, blah, blah, blah. You can do all of that, but I would advise against it strongly because it's absolute overkill. There's a very slick, sort of easy way to do this. Namely, if you think about it for a little bit, you'll see that claiming this is actually equivalent to claiming that this square here commutes. And again, I'm using that beta corresponds to the bar construction. So this square here, what's going on? So it's a bit funny. I'm using the left adjoint functors associated with beta. So that's the bar constructions here. I'm using the right adjoint functors associated with iota. Okay, so this square, it mixes right and left adjoint functors. So in this case, there's always going to be some canonical like lax commutativity. There's always some Beck-Chevrolet type transformation from, I guess, this composite to this composite. And I'm just claiming that that canonical transformation is invertible. Actually, in this case, that is very simple to check. Like I'm just saying, if you perform the bar construction on an En+1 algebra, like I'm just using one of the E1 thingies, then after I forget like some other E1 thingy and I perform the bar, that's still the same bar construction. Like you just have to make sure that like your beta and your iota use two different E1 coordinates, so to speak. And there's really not anything going on in this diagram. Okay, so checking that this commutes is very easy, and I'm claiming under this correspondence between beta and bar, that actually is equivalent to claiming this. Sorry? How does it even relate to claiming that? So, okay, here's the thing. So let me start with a free algebra over here, okay? So that will look like En+1 composite. I'm gonna write it down for you, okay? I have plenty of time, I think. Let me start with a free. Should I write on something I have a witness? On some spectrum X, so I can suggestively write that as En+1 composed X, where I think of X as a symmetric sequence concentrated in degree 0. Okay, so then I can look at where that goes under iota upper star. Well, iota upper star doesn't do anything, it just regards the thing as an En algebra rather than an En+1 algebra. So it still goes to En+1 times X, and then I can go bar, which is beta shriek. Well, what does beta shriek do? It pushes forward along this operad map. So what does pushing forward mean? It means that you form the relative composition product. Okay, so that's what beta shriek does, and then you can chase around the other way. So you can bar this. So if I push forward a free algebra along an operad map, I get a free algebra. I just get the free algebra for this other thing. And again, this does nothing. So it's saying that, this the commutativity of this square is saying that this is this, and since X is arbitrary, it's right. So okay, I did a proof. Good. Is that? I forget. Other questions? Yeah.
You have EN on the left or
Did I mean an EN on the left?
on board?
Oh, yeah. No, I didn't. I mean this thing, but regard it as an EN algebra, right? So this, I'm saying like these forgetful functors, they don't change the underlying objects, they just change the way that you're regarding said object. Like we're regarding it as an EN, one algebra here, I'm just forgetting part of the structure and regarding it as an EN algebra. And that's why this thing comes up here, right? I mean, yeah, that's why this expression shows up. Okay. Right, so that's a composition square, fine. Now, this is sort of the basic building blocks that I'm going to build all sorts of other composition squares with. Once you have one, you can start gluing them horizontally and vertically to get other composition squares, and that's what you can do. So from this one, I'm going to get more. So you can do all sorts of things, but let me just give some examples of ones that are useful to consider. So here's one. What I'm going to do is I'm going to take this composition square and stack them vertically. Okay, so using the maps beta, I can build like a long vertical tower of these things, and I can even take the inverse limit of that tower and still get a composition square. Again, you have to think about why an inverse limit would commute with this composition property, but again, in every degree, all the relevant programs are going to be finite, so no worries. What do you get if you do that? Well, I re-index slightly, but if you take the inverse limit of these betas, as I said before, you get a spectral Lie operad. So here I get a spectral Lie operad, same for the other column. At the bottom, I still have this inclusion morphism of En-operads, again, slightly re-indexed, so maybe it's this one. So, and at the top, well, I get the inverse limit of these iotas along the betas. You have to think a little bit, but you can check pretty much using the thing I claimed before about this diagonal, that this is the suspension morphism for the spectral Lie operad. That's the thing that comes out. So you get a composition square like this, okay, fine. What you can do now is you can take this one and you can start stacking them horizontally like this. Like I could continue along the suspension morphism, and here I could continue along these iotas, and here's what you end up with. So if I continue along the iotas and take the co-limit, then I get the map En to E infinity. If I do it at the top, well, I get the co-limit along these suspension maps in the Lie operad. Well, if you think about that a little bit, you'll easily see that you just get the trivial operad. In all positive arities, you just get something that's infinitely connected. So this that doesn't do anything. So this one just denotes the trivial operad that is the sphere spectrum in degree 1 and 0 everywhere else. Okay. So the upshot is that, okay, here I have another composition square. So it's a composition square that maybe is familiar. It's the thing, like the classical relation between the Lie operad, the En operad, and the E infinity operad. Or maybe you want to specialize to E1. It's the relation between the Lie operad, the E1 operad, and the E infinity operad. So let me just zoom in on some special cases. So here again are these two composition squares that I just wrote up there. So here's a further specialization of the second one. So I look at the case N is 1. I get this square that says, okay, I have a composition like this. So Lie, associative, and com. So again, I'm only claiming that this is a composition square. This is not a push-up square. Okay, so this is a bit sometimes confusing if you look at the literature. Classically, if you think about actual operads, you can get a push-up square that relates Lie and associative and com. That's not a homotopy push-up square. So sometimes you'll see this thing called a cofibration sequence in the literature. You should not take that very seriously. It's a push-out, but it's really not a push-out in a homotopical sense. Okay, that's kind of important. This is provably not a push-out, and one way to check that is, for example, to compute the homology of this square in terms of in the sense of operads, if you perform the bar construction of this square, you do not get a push out of co-operads, as you can usually check. And, okay, anyway, enough said, it's a composition square. Anyway, what does that buy you? Well, essentially saying that this thing is a composition square, it's giving you the PBW theorem. You can classically formulate the PBW theorem in this way, you can do it here too. So what this implies, in a rather formal way, is that if you have a spectral Lie algebra, then this square allows you to, well, this produce a filtration on the universal enveloping algebra. There's some natural filtration that you can associate, whose associated graded is the free symmetric algebra. And here I'm writing the free symmetric algebra on the desuspension of L. That's just, the grading shift is just there because this spectral Lie operad has its bracket in degree -1 rather than in degree 0. But otherwise, this is, up to degree shifting, this is a version of the usual PBW theorem. And if you really would apply this in the case of rational spectra, it really reproduces the classical PBW theorem. Okay, so this is one way to phrase such a thing for in the spectral case, in the higher algebra case, and in some sense you could interpret all of these squares as giving you forms of PBW theorems like this. Maybe another one, this is related to something Thomas was saying. He gave a different proof of this also for a different map, or for a different wrong way map. But if you look at this square, you put n as 0, you glue a few of them horizontally, you'll end up with this square. So as the right map, you have, again, this sort of beta, or this infinite composites of beta from the Lie operad to En, and it's saying that this particular square is a composition square. So that's this equation that also featured on Thomas's slides. And he gave a proof of this using the Goodwillie calculus, taking the derivatives of the function sigma in the loops n. This is a different one that you get from this yoga of composition square. All right. Maybe one thing that's worth pointing out is that this equivalence actually immediately implies the following formula for the universal enveloping algebra. It tells me that the universal enveloping algebra is the Chevalier-Eilenberg homology of loops N L. Maybe just quickly go back to the previous slide. So what I'm saying is that the universal enveloping algebra is what you get if you start with something over here, like an algebra for this operad, you push it forward here. But saying that this is a composition square, again, it gives you this square of functors. It tells you that you could have also computed that object by first pulling back along this morphism of operads. That's essentially taking loops n of the thing, and then pushing forward along this map of operads, which is pushing forward from L to 1. That is taking homology with respect to Lie algebra, Chevalier. So this equation is a direct consequence of this observation. And this in particular shows that this way of dealing with the universal enveloping algebra agrees with what Ben Knudsen does. So you look at Ben Knudsen's paper, like he gives a construction of a functor un, which is very different. It uses factorization homology, very different setup. And in the end, he proves a theorem, which is, I think, one of the central theorems of that paper, that says that his construction satisfies this. So this tells you that the two approaches will agree. Okay. Any questions at this point? Do I need to get out of here? No? Yes, you are, okay.
Is there a way to interpret these composition squares in terms of the chain rule from?
I mean, some of them, yeah. I mean, in particular, like this one, yes. It's like you want to think of this, the functor corresponding to this is sigma infinity, the functor corresponding to this is loops n, and so you can, so this is the proof that Thomas more or less outlined. And for all of these, you can start like, for these ones, yeah, I don't know. You can try to do some pattern matching with functors that you can write down in the categories limited spaces, and presumably most of these, like by choosing the functors cleverly, you could also get from the chain rule. What? Right. Okay. Yeah.
So when we get bimodal equivalence between En and En minus 1.
The composition product.
Yeah, it's composition product. And so you were asked if it's an opera thing. But again, so I'm thinking in algebraic terms, but so you can have in algebra a distributive law between the and is there this notion of distributive law between
I would love that, and I don't know. But yes, in algebra, if you have, exactly as you say, if you have two operads, you could take just the composition of the symmetric sequences, and you can ask, how do I put an operad structure on that? Like that, yeah, what you do with Lie and Com to build the En, and you have to write a distributivity, plus it has to satisfy some axioms maybe. And I do not know how to do that for operads and spectra.
Because for Lie and Com, you can do both, and
Yeah.
one you get associated and the other one you get Poisson.
Yeah. Yeah,
So
and yeah.
that was kind of interpretation of the special case of one.
I agree, yeah. I mean, it's an excellent question, and I don't know how you would sort of lift that idea to higher algebra. I don't have a good way of doing that. But it's closely connected to this, yeah, this thing that came up that in that square, like something is a bimodular equivalence, but a priori you don't know why it's an operad. Yeah, and, I don't have something good to say about that, but it'd be nice if someone did. Right. Okay, so what I'd like to do now, because well, there is time, I'll go back to the theorem that I started with and try to say something about how you actually get it, like where it comes from, because in some sense, like this is where all the calculus happens, and also the equivariance. Mike Mandel said on Wednesday that this was a conference about N-infinity operads. I have nothing. This is not about N-infinity operads. It uses equivariance in a very mild form, and it uses a bit of visual calculus. That's all I've got for you. Right, so this was the statement of the theorem. This functor is fully faithful on these En operads and the suspensions. So how do you go about proving such a thing? Oh, that's a bit fast. Well, first of all, this statement follows from a more basic statement about this association of a functor on spectra to a symmetric sequence. Right, so I already wrote down this thing before. If you have a symmetric sequence, then you can construct an endofunctor of spectra that assigns to a symmetric sequence A, this thing that I was denoting sim A. 5 minutes. Oh, this clock is not. Okay, thanks. No, I was miscalculating my time. We'll see. So the claim is this is fully faithful on the ENs, just thought of as symmetric sequences, and their D suspensions. So how do you do that? So really the goal here is to show that natural transformations between functors like this for particular A's actually have to come from just maps of symmetric sequences. So really what I'm saying is that if I have two symmetric sequences that are like En, there's some shift of them, then I want any natural transformation between the corresponding functors, these free functors, to be just a direct sum of homogeneous pieces. Okay, so a priori, if you think about this for general symmetric sequences, there's no good reason that that should be true. And for general symmetric sequences, it isn't true, right? So, but I want that to be the case in this for A and B of this special form. So I'm introducing a little bit of notation in illegible color, my apologies. But what this says is dKA, so just it's notation for the kth extended power with respect to the symmetric sequence A, and this thing I'm calling dKB, so the kth extended power with respect to B. So that's just abbreviation for these homogeneous functors that you associate with a symmetric sequence. Okay, so I want any natural transformation like that to break up into these homogeneous pieces. So what do I need for that? Well, if you think about it, what I need to prove is that if I look at a natural transformation from an individual one of these dKs into this big direct sum, so this is just this formula for sim B, then I need that to pick up just the kth homogeneous piece and not map into any of the others. Okay, so I just want to warn you, like if you're familiar with calculus, this looks like something that's not so difficult. But this is a stronger statement than asking that just there are no natural transformations between the individual layers, right? Calculus will tell you there aren't any of these if L is less than K. You can try to use dual calculus to show that there aren't any when L is bigger than K. And if B is nice enough, then that dual calculus argument will actually work. It's something about tape vanishing for things with respect to B, which the En-operads, they have that feature. That's good. That's not enough because you have to somehow commute out this direct sum, and that's actually the most subtle part of the argument, getting rid of that direct sum. So that's where the meat of the argument really is. It turns out, if you think about this carefully, that the condition that becomes relevant to prove this statement is that the symmetric sequence B has what we call nilpotent Euler classes. So what does that mean? Okay, let me try to explain that briefly. So by Euler classes, I mean the following. I just take a finite set T and I look at the reduced standard representation of the symmetric group of T, right? The thing that featured before is RT modulo the diagonal. So then you have something, I'm just calling this the Euler class. It's just this canonical map that includes the fixed points 0 and infinity into the representation sphere for that representation. You're going to denote that by ET. I mean, I guess A is also sort of standard notation, but I'll use E for it, okay? Then a symmetric sequence is said to have these nilpotent Euler classes, precisely these maps ET, they act nilpotently on the spectra AN, and they act nilpotently with a uniform bound, and this uniformity is what's important. So I'm saying there exists a constant such that for any n and for any subset T of 1 up to n that has cardinality at least 2, this Euler class, if I take its C power, so the C is this uniform constant, if I take its C power on N, this is sigma T equivalent in null. And the point is that the C is independent of N and T, it should be uniform. So this somehow is, if you go in carefully, this is the thing that allows you to prove this theorem. So this allows you to carry out that argument that I sketched that you wanted to carry out. So if you look at symmetric sequences with nilpotent Euler classes, then this function is fully faithful. And the ingredients for this proof, as I already sort of outlined in words, are Goodwillie calculus and dual Goodwillie calculus. You have to go in sort of carefully and think about the way that, you know, dual Goodwillie derivatives are computed, and you can use these nilpotents of these Euler classes to show that certain inverse limit systems are like, pro-constant, like nilpotent in a very strong sense. And that's what you need to commute a limit past the direct sum at some point. Okay. So that's statement 1. So that's where you sort of feed into that theorem that once you know that the En-operads have nilpotent Euler. Okay, so these two statements combined give you the theorem that I told you about the En-operads. So this is the theorem where the meat is, like this is where you have to come up with an idea and prove something. Once you know that this nilpotent Euler class is the condition that you're looking for, this is very easy. Like this is not a big deal, and the proof is just an exercise. Like once you know that this is what you want to do, for the En-operads, it's simple to show that they have this nilpotence property. Actually, you can just write down a very explicit map, just a null homotopy of this thing on the nose. Like this is, it's an exercise you could give to a somewhat skilled undergrad. The hint is the Euler classes are actually nilpotent if exponent exactly n. Like it's sort of a major hint that will be enough to figure out what the map is that you want to write down. But this is just completely explicit, no homotopy here, no nothing. So okay, that's how you prove this, and I think that's also at the end of my slides. Yeah, sure.
So it says it's fully faithful on things with important Euler classes.
Yeah.
Did I miss something, or do you just need the target of this?
Yeah, you just need it for the target. If I want to say it's fully faithful on a category, blah, 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 then I need it on all of the objects of that category. But you're right, you only need it on the thing you're mapping into. Yeah, that's correct.
And do you have other examples, interesting examples which are other?
No, I mean, we were trying to do something about EN, so that's the thing we focused on. I mean, that's a very sensible question, but I haven't looked for many other things. I mean, yeah, I said this to Michael before. Somehow my standard library of operas is very small. It's like En, Li, and Com. You know, that's what I do. So yeah.
How sharp is this condition on a little bit? Like, does that characterize the things where this is kind of easily?
I don't know. I've got no idea how to prove anything if you didn't assume this condition. But yeah, well, I mean, maybe I should be a little more precise. Actually, I mean, the inspiration for this argument comes from the T-n local context. Like in the T-n local context, this theorem is true unconditionally, right? You don't, this symmetric sequences in the end of functors of the T-n local spectra is fully faithful done. And the proof uses tape vanishing, but it uses that, so Euler classes are not necessarily nilpotent in the T-n local setting. But you use the fact that if you smash with a fixed type n complex, then Euler classes always become nilpotent. In the T-n local category, you can always prove something is an equivalence after smashing with a finite complex, and so you can always pretend that Euler classes are nilpotent. Well, they aren't actually. So in that setting, actually, you do have, for example, there you can apply a theorem like this to the Lie operad, where you don't have nilpotence of Euler classes, but you have this replacement for it. So it wasn't trying to take that result and apply it in this case that we found that we actually needed. Like, you don't have this trick of smashing with a type, you don't have tape vanishing integrally, well, or you have for these operads, but that's not enough to get this nilpotence argument going, and so you just have to assume the nilpotence from the start, and it turns out to work for the En-operads. So, you know, but other than that, I wouldn't know what to do.
help to understand a bit more what our happening?
I don't think so. I mean. Yeah, I mean, you can say, okay, it's okay to study automorphisms of the category En-algebras, but then I don't see why that would be, yeah. It didn't help me understand the maybe that's the, thing to say, maybe.
That's good.